Okay, we're here today on September 7th, 2023 with Professor Marco Castaldi at the City College Chemical Engineering Department. Good morning, Marco. It's nice to see you.
Hey, good morning, Stu.
Okay, so what we'd like to do today is to get a session where we hear something about your life at CCNY, your group, and so on. So to get started, why don't we talk about how you got here? What was your path to getting here?
How I got to CCNY. It's actually a very personal story for me, and I tell you briefly. When I graduated from UCLA in chemical engineering and combustion, thought, should I go for academic or industry? And I thought, okay, let me try academic, and of course I'm a New Yorker, so I wanted to get back to New York, and City College was always very familiar to me. It's a very well-known institution here, not only within New York, but kind of the Northeast and a little bit further. And sent my resume in, and what was really nice was I got a phone call from a chair that said, Bob Pfeffer, who said, you know, you got a great resume, great background, great work that you've done, go get some industry experience and call us. Okay, thank you very much. So that helped me make a decision, go to industry and get some experience. So I went to work for a small company, Precision Combustion, great experience. I was there for about 6 or 7 years. Did a lot of work with combustion, catalysis, catalytic combustion, worked with components for bigger companies like GE, Siemens, Westinghouse. And then after being there for about 6 or 7 years, I said, let me see what teaching's about. I started adjunct teaching at Manhattan College to get an idea. And I thought, yeah, I think I do want to still go into academia. So leaving PCI, I decided, let me send a chance for a job here at CCNY. And there again, a great response in terms of a chair, Irv Renard, contacted me and said, you got a great resume, you got a great background, you got industrial, something we're really looking for. Can you wait for 2 years until we can open up a position? And I said, no, I'm sorry. I said, I need to make the move. So I took a position at Columbia University in 2004 in the environmental engineering department. And I was there for, again, about 7 years or so. And time to maybe move. I really wanted to get back to chemical engineering. And I said, okay, one more try. And I sent the letter to CCNY's chemical engineering saying I'm looking for another position. And chair called me back, Alex Kuzitz, who's the dean now. And he said, don't make any decisions. We're going to get a position. Let's talk. And sure enough, in 2012, I made the move to come here, kind of back to my roots of chemical engineering, but finally at City College.
So the industrial background really helped you. The mixture of the two seems to have been a really interesting thing for you.
Yeah, I would say the industrial background, personally for me, if I didn't have that industrial experience and along the way as I developed my research at Columbia and then of course even expanded it further here, I kept in touch with these industrial contacts. And you know, right now about half or maybe a little bit more, 60% of our funding comes from industry. So, you know, companies, small startup companies that you maybe never heard of, like in Enerchem, all the way to companies like BASF, Waste Management, the American Chemistry Council. So that industrial experience for me really helped because it helped me understand the difference between fundamental research and what I would call applied engineering research. Research to solve a problem for industry, but then also research in terms of fundamental to kind of understand it and interrogate some fundamental aspects.
So being on this academic side now, have you had people that have worked in industry for a number of years come and apply to this department and to get a degree, a higher degree, and have the mixture done that way? Has that been possible?
Yes, actually my group the personal experiences that I had was, of course, students that come out of undergraduate to go straight to grad school. But I've had a couple of students where they were working in industry, they wanted to continue their education, did their master's, of course that's easy to do, but then signed on for a PhD, and they stayed at the company doing their coursework with the PhD, and when it came time to do research, they either peeled away from the company a little bit, or we developed a project with the company that they were able to finish their PhD, and two of my students did that. And then of course others, right, they just quit 100% and they come, full-time, and that's a decision what they want to do.
Okay, so can you tell us more about what goes on in your lab as far as work, research?
Yeah, so the research that goes on in my lab, the name of the lab is the Combustion and Catalysis Lab, CCL, and that's because I did my PhD in fundamental hardcore combustion, and then while I was in industry, a little bit in graduate school, but then also while I was in academia, moved really into catalysis, and it's the applied catalysis. We don't synthesize catalysts, we've done that, but primarily what we'll do is understand the reaction mechanisms on the catalysts. We will compare them and screen them and so on, do a lot of testing, and we will interrogate them down to a level of either just how much conversion you get, yield, durability, all the way to do isotope labeling of reactants to understand, which are the real active reactants and which are things like spectators, and where do they sit on these catalyst surfaces. We've done work with Brookhaven National Labs and the beamline to understand exactly what changes on the catalyst metal might be happening. On the combustion side, we still do fundamental combustion. For example, I have a student who is looking at detonations, because there's a large amount of work in understanding detonations in extremely controlled conditions. But we have one of the largest blast chambers where we can put different geometries in there and understand if there is a combustible mix and it happens to detonate, does that attenuate the detonation, or does it strengthen the detonation? And specifically, we're doing work for that with Con Edison. They commissioned us because if you ever go onto YouTube and you look up manhole explosions in New York City,
Right.
you'll see a video, and what they're trying to understand is not only how does that all occur, but how does the strength of these detonations launch a 300-pound manhole cover 150 feet in the air. And luckily to date, no one's gotten hurt on these things, but we're doing those kind of investigations. So the other side of the combustion that we also do is a lot of what I would consider waste to energy. So they're not looking at gas phase or liquid phase fundamental combustion, but more looking at how to take waste materials, literally garbage, or biomass and others, and how to use the inherent energy in there to make either other products. So we take waste plastics and we turn them into precursors for plastics again. That's a nice combination with the catalysis, because after you say thermally pyrolyze plastics and make an oil, we're putting them through a fluid catalytic cracking process to then make olefins to go back to plastics. So there's a lot of synergies in this combustion and catalysis lab, even though they might sound like they're completely different. There's a lot of overlap.
And it also sounds like it's playing into the transition that is going on in all of our lives.
Oh, sure. I mean, one thing that I think a lot of people don't know is garbage that we throw away is 2/3 renewable. So just combusting that in a standard way and making steam and making electricity, you're making renewable energy, 2/3 of renewable energy. But there again, the stuff that we throw away is remarkable because there's a lot of materials that we get back. Copper, aluminum, silver, gold. So we get materials recovery. Most of our work, of course, we get tasks and everything from industry, and we write to agencies like the Department of Energy, National Science Foundation, has a very large environmental component to it. I would say 90% of the work that has gone on in the combustion and catalysis lab since I started has been, of course, to understand at the fundamental levels, but how could those processes be improved, or what kind of environmental impacts do they have? So that's a large facet of the research we do. For example, even in the detonation space, there's a lot of interest in taking, and you may have heard this, things like SAF, Sustainable Aviation Fuels. There's a lot of companies trying to convert waste materials into a fuel, and honestly, they look at it and say, it's got the pour point of a fuel, looks like a fuel, smells like a fuel, viscosity of a fuel. We actually do the testing. We have engines that we do testing on, and what we found is that while some oils actually help the engine to perform a little bit better in terms of a thermodynamic efficiency, they yield a little bit more emissions. And so now the question is, okay, are these fuels that we're making, what is the overall environmental benefit to that? And at least we get the hard data behind it. We see a lot of times that there's a lot less NOx because these fuels that they generate don't have the nitrogen components of a typical fossil oil, but sometimes they don't burn as well, and so they generate a little bit more unburned hydrocarbons. Which one is better and which one is worse, right? So this is the kind of, I think, areas.
It's a very environmentally, in some ways, focused effort that you have.
A lot of it is, yeah.
And so what is it like for a grad student, comes to your lab, is here, decides that they want to work with you? What is it like for them then?
Well, you'll have to talk to the grad students. They'll tell you what it's like for them. What I like to tell the grad students, and I think this rings true, is one thing that's very important is they will have a project that's their main focus, but they will do other projects. And again, just coming from industry, yes, you're maybe a subject matter expert, yes, you're the lead on a task or a project or something, but you are supporting other projects. You are using your skills to support other efforts. So that adaptability has to be developed. And so in my group, every student has more than one project in the sense that they got their main PhD work, but we'll get, let's say, a project coming in from an industry for 3 months. They'll say, we just want to screen this or check that. Okay, this is, if it's a catalysis thing, we'd say, okay, well, the students who are doing catalysis, this is not exactly what you're doing, but it's catalytic, looking at a little bit of a different facet, and it's only for a 3-month stint. Usually we publish a paper from that, right? So it's not like it's just work that gets done and we hand off, go to presentations. So the students that come to my group, 85% experimental. We do have to do some analytical work, whether that's just MATLAB program to process data and so on, or write mechanisms and so on. But we also have done in the past things like Aspen, CFD, and so on. So there's a component of, I'll call it, non-experimental analytical modeling that gets done, even if it's just reaction engineering modeling. But they'll be working in the lab on an experiment. And we, I think, have, again, coming from industry, I know we can buy pieces of equipment that are so automated that you put the sample in, you press a couple of buttons, go away and come back a few hours later, and all the data's there. And then, of course, there's the other side of it where you have to kind of build it all yourself and do it. There's a nice happy medium. And I have really geared the work that we do and the projects that we do where things that the students should put together, like a reactor, where whether it's horizontal or vertical or how you introduce the reactants, very, very important. You need to understand that. So to have that built is, to me, very valuable. But then we use the right analytical equipment. We'll buy all of the GCs, the online analyzers, everything will be mass flow controllers that will feed it, so we're not dealing with rotometers. So I like to think that the work that gets done in our lab is a combination of unique, hands-on building yourself reactors and systems, but with the right amount of equipment to make, when you're done, have a system that's quite robust. And some students will even like automate and program. We have LabVIEW. Some students like to use LabVIEW, so they'll automate everything, and some students don't like it and they just download the spreadsheets and then process it themselves. And that, there's merit to both sides of that. Does that answer, you think?
Yeah, thank you. That's a good answer. So, for example, generally, how big a group do you have? How many grad students, postdocs, undergrads? I know it changes with time, but in general.
Yeah, so again, I like to take from my industrial, and I still work with industry now. I still work for GE Aerospace, so I have some teams under me. I purposely try to keep the team, I think it's considered small, anywhere from 4 to 6 PhD students, one postdoc. I have a center, the Earth Engineering Center, that really we can talk about later, but that's really where companies come in and they want 1 month worth of work, 2 months worth of work, and who knows what's going to come out of it. It's almost like a survey, sometimes a literature survey for them. And they all have engineers. Like there'll be a student who have graduated with their bachelor's and they're looking for a job, they'll work there. So they all have maybe 1 or 2 engineers. So in total, the group size, and of course we have undergraduates. We have undergraduates that come in. But the group size has never really gotten more than 10. And I would say in terms of the PhDs, it's between 4 and 6, because that's where most of the focus needs to be, and that's something that I think we all could handle. We work very well as a team, though. It's not just me. The postdocs, the more senior students work very, very closely. We have a very good culture in our group.
Very good. So in general, how do your students, is part of the reason that they come here, does New York have an appeal, is what I'm trying to ask. This is a very vibrant city, it's a very busy city. What are the students, and we'll talk to a few of them later, but how do you feel? Like, is it an advantage to them, or?
Well, okay, first of all, New York City is the center of the universe, and so how could it not be? I would say there's a couple of facets to that. One is, you're in a city that, there's no dorms here. So, however, many students live within a 2 or 3 block walking radius because there's just so much around. We're in historic Harlem and right next to Alexander Hamilton's house, so that's great. Or, just a subway ride, you're down in Lower Manhattan, near Times Square, even some of them even going to Brooklyn. That's a little bit too far, I think, but they go there, Queens. So there's a lot of options in terms of living in the city in what you want to experience. To me, the real big attraction is you've got multiple universities around here, and we have collaborations with all of them. And so what I like to tell the students is that coming here, you're literally limited by your imagination. That if there's something you want to do, we could get a collaboration that's close. First of all, City University, CUNY, has one of the most advanced, research centers. It's called the ASRC, the Advanced Science Research Center. And that is where a lot of the schools, Stevens, NYU, Columbia, send their students to do research. And this is on our campus. So, if you're intimidated by a big city, there's opportunities to stay close. There is a dorm here, but usually gets filled up quickly. But if you want to have some level of a city experience, it really is what you make of it. And I would say the the students that come here, I think, have an element of wanting to be in New York City, but I don't think that makes or breaks their decision. I think most of the students, at least that come to me, for sure, because I've gotten individual requests, but students that come to CCNY, it's the work that's going on at CCNY, it's what CCNY has to offer, and then it's in the city, and they can take advantage of aspects of the city for there.
So could you give us a little rundown of some of your former students and where they're at and what they're doing now once they've finished up in your lab?
Oh yeah. One thing I will say that me personally I'm very proud of is every student that has graduated has had more than one job offer. And again, what I specifically pay attention to is when a student graduates, I don't want them to just take the first job offer they've got. I have forced some of my students to go visit other companies, even though they had one that they wanted to go. I said, no, you need to see what's out there and make an informed decision. Because to me, the end result of all of this is not that you get your PhD, not that you really do a lot of work in interesting areas, not that you learn a tremendous amount, but that you're going to get a job for the rest, for most of your life, or the career that you're going to make. You really enjoy what you're doing. The groups that we've had, the students that we've had in the past from the group, I would say 20% of them are in academia. I've got a student who's a faculty at Korea, student who's a faculty in Cooper Union. The other, 80% are in industry, in companies. One student who was very high up in ExxonMobil did very well. He actually just left and started his own company. And I think, there's a little bit of that entrepreneurial spirit in our group. Not only are we working with small companies, doing some research, but, you get ideas. But I've got students that are at BASF, at GE Aerospace, working at waste management. So Clariant. And so I would say that the students that when they finish usually take a position that is in chemical engineering, but like a little bit, it's not typical process engineering that one might think of, or petroleum engineering. I've got a student that's working at like the American Chemistry Council, right? And there you need some hardcore understanding of what goes on and how to make plastics and so on, but there's a large, policy aspect to it. But these are some of the companies, like I said, BASF and ExxonMobil.
So it's a really varied assortment. They have opportunities in many different places.
Right. And the key, like I said, is that I allow, so first, because they've done some research for companies, already there's an exposure to that. And that's another thing I want to...
Do they interact at all with the company?
That was something else I was going to say. Again, coming from the kind of background and experience that I have, I understand I cannot always be, and I don't want to be, the face, the interaction, the communication to the company or to the agency. The students who are doing the work, they're the ones that give the presentation, that give the debrief, that when the company comes, they work with them. And so to me, it's all about making sure that they get that one-on-one or get that exposure, get that interface with the customer, whether that customer is the NSF, the DOE, or BASF, or ExxonMobil, or whoever it is, that they get that interface, because this is what's going to happen. They're going to have to work with these types of people. So they really get, I think, the right exposure. And then when it comes time for them to start looking for a position, they have an idea of what they like and what they don't like. They've had some interactions with some companies. I know one, I'm not going to mention the name of the student of the company, but one student that worked for a very well-known large company did some excellent work, and he was interfacing with them, and they had some, real demands, and we were able to keep up. But in the end, he said, that company does some great work, but I'm not sure if I really want to work for that company. And that's very valuable, because at least you know what you don't want to do, and that's good.
So, to sort of come to a conclusion here, so what would you recommend for someone who's taking a look at this and thinking, yeah, maybe I'm interested in considering CCNY, maybe I would like to work with Professor Castaldi. Is there some way they could, what makes sense for them to either get in touch with you or to learn more about what's going on? What would you recommend for them?
Sure. So the best thing that a student must do is visit. Have a conversation. So send me an email. This is the easiest way, of course. We could have a conversation and phone call, but you have to come and see the lab. You have to come and see the place, because you can really only get so much, from kind of afar. And I know a number of students that have come and they were on the fence, and not just me, but really within our department, and they came to visit, and then you have to talk with the students that are here, right? These are the ones that are living, breathing it, going through it, and they're going to give you, their experience, which, is different, right, than my experience. I mean, I'm here, and these students have just come or have been here for a while. So definitely feel free to reach out to former students. We have a great web page, CCL, and there's all the former students there. A lot of them find each other through LinkedIn. But then you could contact me, of course, directly. We could have a conversation. And then if there's real interest, I would recommend that they come visit. Could I add one other thing?
Yeah, certainly. Before we finish, please add whatever you'd like.
One of the things that's important in this day and age, and I've recognized this, very fortunate I recognized this many years ago, is the work that engineers do, especially chemical engineers in the type of area we're in, combustion catalysis. It's very international. It's global. And one of the things that I do in my group is I make sure not only that these students have these other projects and so on, but that they get to not just go to conferences, but get an international experience, or I'll say get an experience outside of my lab. We have collaborators around the US, and we have collaborators around the world. And students will go to the collaborator for 3 months or 6 months, and they're doing research there. It's not an overlap. They might have some equipment or some activities or things that we don't have, so it's complementary, and they can do some tests and measurements, but then they learn other skills, of course, but then they get to live in places like Italy, France, Japan, Brazil. And except for the poor students who went through the pandemic, every single one of my students has had an experience outside this lab, either to Chicago or to Japan or to Italy or France. And I think that's a huge benefit.
I couldn't agree more. Having done it myself when I was a postdoc, it was a life-changing experience.
Yeah, and you get to understand how to interact with these different groups and cultures and how they think, right, a little bit differently. Yeah.
Okay, well, Marco, thank you so much for spending the time with us today. And I hope the prospective students that may watch this get a good flavor for, how interesting and fantastic it would be to come and work in your group.
Great. Thanks, Stu.
Okay, so I'm here today after we've spoken with Professor Castaldi with 2 of his graduate students, and we just want to get a little bit of feedback. So can you each just tell me in a couple of sentences, how long you've been here, what kind of things you're doing, what's your life like been here so far, and then we're going to go with you into the lab and see some of your experiments.
Sure. Would you like to go first, or do you want
So please tell everybody your name and...
Yeah, hi, I am Janvi Trivedi, and I am 4th year PhD student. I have been in City College since 3 years. I started in 2020, and first I joined a computation theoretical group where they used to like study interfacial phenomena, and after 1 year I was like not I didn't like working theoretically that much. So I decided to change my group, and I spoke with professors, and I liked Professor Castaldi's work, and it was like more hands-on and experimental, and his work is on combustion and catalysis, and focuses on waste to energy, and I liked that research, and I decided to work in his group. And it's been great working in his group, and also in City College Chemical Engineering Department. Everyone here is very friendly and very helpful, and I enjoy my time here.
Okay, thank you so much. Okay, Caitlin, now we'd like to hear a couple of words from you.
Sure. Hi, I'm Caitlin Lawrence. I also joined the program in 2020, like John V. But unlike John V, I joined Professor Castaldi's group right away. My work here focuses on using waste to energy ashes, so the solid residual that comes out of combustion with energy recovery processes, as a catalyst for NOx reduction. So our interest is in attempting to replace expensive selective catalytic reduction catalysts with something that's much cheaper and might well do a similar job to it.
Okay, good. And what have your experiences been in this group and in the department?
Yeah, my experience in the group has been great. We've both been able to travel a lot.
So where have you gone? Where you've, Professor Castaldi talked about having opportunities outside the U.S. even to spend time and go conferences, maybe even spend some months. What's been your experience?
So last summer I was able to attend a conference here in New York City, as well as one in Copenhagen, Denmark. That one is a waste engineering conference that takes place every other year, and is usually in a different European country every time. Then this past summer I was able to go to France for a month to work in a different lab in a small town called Albi, right outside of Toulouse. And then we also attended a conference in Milano, or right outside of Milano. And there we were able to tour a recycling center in Europe, which was quite interesting because we've also toured a recycling facility like right outside the city. And the American versus the European way is quite different in very interesting ways. And then we were able to also tour like an industrial composting facility, which was really neat.
Good. Sounds like you've both had really good experiences.
Yeah.
Okay, so now we're going to take off and go into your lab and see what's cooking there.
Okay.
Okay, so this is where we have a couple of labs that we have here at the CCL, Combustion Catalysis Lab. This is what I would consider maybe the main working lab that we have, and this is where a lot of the catalysis work goes on. We have anything from what we might consider workhorse type of equipment, BET, TPR, and so on, all the way to things like the TGAs and the GCMS. But then, as you'll see around the lab, we have a lot of individual constructed components, you know, such as the reactors that the students build. And again, the important aspect that they build is the one that basically is for how the configuration, the introduction of the reactants are important. That's something that they would build. So this is something, and Caitlin and John B will talk to you about, but this is something that Caitlin built, but it's connected to, you know, what we consider the state-of-the-art type of analytical equipment. So this way, the system is put together correctly. Caitlin knows, you know, what are the important components and what really impacts everything. But then, of course, doesn't have to spend a lot of time doing, you know, built-up analytical equipment. It's the standard stuff that you would use in industry, in any lab that we have. And again, one of the things that I'd like to make sure the students and the team and the apparatuses have
are pieces of equipment that are standard in the industry. They'll find them in the industries, you know, when they go to work for companies or if they do research in other places.
Okay. I think now we're going to let Caitlin sort of run through her life in this lab, and what she does, what it's like. So tell us about your equipment.
Sure. So I'm interested in understanding whether or not ash from municipal solid waste incineration can be used as a catalyst in selective catalytic reduction and other NOx mitigation, NOx abatement reactions. So currently I have ash staged in this reactor. It's hot, so I won't open it, but it's just a standard quartz tube with a little bit of quartz wool to support the catalyst bed. And then on top of it is 4 grams of sieved ash. I take the 125 to 212 micron particle size fraction to minimize issues with mass transfer limitations. Inside is a thermocouple that is placed directly in the center of the bed. And that thermocouple is connected to the data acquisition unit that I use to measure all of the different instrumentation's readings at any given moment in time, and also to control the 3 mass flow controllers that I have here. The 3 mass flow controllers are dosing in set amounts of the gas from these cylinders here, as well as a gas that I store in a flammable cabinet on the other side of the lab. So this gas here is nitric oxide and argon, and then I also have oxygen and argon. These are both at ppm levels so that we can simulate the flue gases that are coming out of the back end of a tailpipe of a car, for example, or a stationary source, such as a cement kiln or a waste energy facility.
So how was it building all of this equipment? What kind of experience was that?
It was challenging for sure, but I learned a lot. In particular, I learned very quickly upon starting to build all of this that my electrical engineering skills could be a lot stronger. And so it gave me a really good opportunity to revisit all of those physics 2 concepts that weren't so strong and relearn how to, wire everything and ensure that I have the right current and the right resistance in all the different places that I needed to be able to measure everything. And then it's been a test of my just basic transport, chemical engineering transport knowledge also, because you need to make sure that you have no leaks and that you have the right flow coefficients through all of your valves and that all of your pressure transducers are in the right operating range. So it's definitely challenging, but it's a great learning experience for any young chemical engineer as well. But yeah, I guess I can finish explaining what happens when the products come out of the reactor at the bottom here, because it's a downflow system. They come and they're sampled by micro-GC. So micro-GCs in general, their standard purpose is to just separate gases and allow you to quantify your products. But this one in particular uses 2 different carrier gases, argon and helium. Those are also pretty standard. And basically it just lets us know how much this current method is designed to let us know how much nitrogen, oxygen, hydrogen, nitric oxide, and CO2 and ammonia are in our product gases. So it does a great job of giving us these little outputs here. As you can see, this is only nitrogen, which is great because I'm only flowing nitrogen right now, so I know there's no contamination. And I know that my sample is done off-gassing any oxygen that might have been weakly adsorbed to it. So yeah, it's done heating up. It's at a steady 200 degrees. You can see that. Okay, just press this button. So here we see we're well controlled within 2 degrees plus or minus 200, and we have a steady flow of nitrogen. And now we'll switch over to reacting gases for the rest of the day. This is pretty much what I do every day. I come in, I let heat for 2 hours, sometimes closer to 3 if I'm going higher, and then I switch over to reacting gases. I let it run until it's at steady state, and then I cool down for safety.
And the
yeah.
goal is to see whether you can do abatement of some gases?
Correct.
Okay.
The goal is to see whether or not we're actually taking NOx out of the reactant stream.
By using a catalyst or?
Yes.
Yeah, okay.
Well, by using a non-conventional catalyst.
A non-conventional catalyst. Okay, and where do you get those from?
We get them from a waste-to-energy facility, but technically if we wanted to, I could show you this. This is municipal solid waste. Well, this one's actually, it's 25% plastic, but it has a little bit of biomass in it as well. This is
Wow.
a good, I guess, example of what like standard garbage looks like homogenized waste.
Okay.
So if I were to burn this, and the solid residual that ends up being about 22% of the mass of the original, that 22% is what I'm putting into my reactor.
Yes.
And because we know that it has metals and things in it, we expect that it may be catalytic, like a well-engineered catalyst.
So it has its own catalyst in it? You're not adding a supplement?
I'm not adding anything.
Oh, okay, cool.
Yeah, thanks.
Okay, well, thank you so much for explaining that to us.
Of
Appreciate
course,
it.
of course.
Okay.
Hi, I'm Janvi Trivedi, and my project is on recovery of materials from waste to energy ash. As you all know that there are about more than 60 elements present in the waste to energy ash, which is normally landfill, and we have to import materials from outside US. So instead of importing materials, we can recover materials from the waste to energy ash. And to do that, we need to understand the thermal behavior of ash first. And to study the thermal behavior, we use this equipment called thermogravimetric analyzer, that is TGA, where we put in the ash sample in this crucible. The sample goes in here, and there is a weighing scale which measures the mass loss of the sample as the temperature increases, and we get a mass loss versus time and temperature versus time plot, which we can see here in this computer. So this is the TGA plot, this is the mass loss versus time and temperature versus time, and from this we can calculate the mass loss of the sample at specific temperatures, and we can predict the reactions that take place in the ash at elevated temperatures. And when this TGA is coupled with micro GC, as Galen mentioned,
So
that
you can analyze the gases.
so micro GC separates the
Where is that?
gases. This
Oh.
equipment. So micro GC separates the gases that come out from the TGA, and then you get the composition of the gases coming out, and you can analyze those gases and also predict the reactions that takes place in the ash, and that helps us understand the behavior of the ash and how we can recover the materials from the ash.
Okay. And what have you learned, in the time that you've been working with this?
Also, I have learned different characterization techniques that are not example is TGA and also in other CUNY campuses, and it's great to learn those techniques. Like I have learned a lot of techniques like XRD, SEM, EDS, and how they can be useful to characterize not only ash but different powder materials.
Okay. Well, we thank you very much.
Thank you.
Thank you for showing us your world here.
Hi, my name is Erica Razou. I'm an undergraduate student at City College. I'm in my senior year, and I've started working with the Combustion Catalysis Lab and Environmental Engineering Center over the summer. So the project that I'm working on right now is in collaboration with BASF, which is a very large chemical company, international, and they're trying to look at how to incorporate a greater percentage of bio-oils, oils made from agricultural waste or trees that fall down, renewable sources of energy into fuel and how we can integrate those kinds of oils into our energy system for more sustainable energy source. So we're looking at several issues. One is the sustainability of these mixes of oils. And in particular, I'm looking at how these oils will interact in a very, very fast heating environment. So as to imitate the type of reactors that refineries and other producers would have in place, we use this thermogravimetric analyzer. We preheat this furnace up to very high degrees, so 1300 degrees Fahrenheit. A small pan is used to collect a small amount of sample, and you can just see how small these pans are. This was what will contain the oil and any catalyst that we're testing to see the impact of on the oil. This small pan will go right in here, get closed up into this glass vestibule, and will slide into the furnace when the furnace is extremely hot. The reaction that then takes place takes only seconds, and about...
So you place it already into a furnace that's already at
already
temperature.
hot. Yeah, because we're trying to imitate what the oil will experience in an actual like refining setting. So when this goes in, this is at about 1200 degrees Fahrenheit. It's very hot, and we're trying to get the sample up to about 1000 degrees Fahrenheit to imitate, large-scale production facilities. So when that happens, you'll see smoke and everything, and I'm recording all the results using this software. So this shows us over time the mass loss, and that's what this instrument does. It measures thermal change, so temperature change, and the associated mass loss.
Right.
So you can see on this last sample I ran, there was a 62%, 62.6% residue of this sample, and that sample is actually here. So you can see that what's left in the pan is a combination of the initial catalyst mass, so that's about 50% because we did a 1-to-1 ratio of catalyst to oil.
Oh, okay.
And so the remaining residue, which is a coking, is about 12.6%. Should I take it out? This is the residue. So this what's reflecting, what's on this chart is the 62.6% residue. So we're doing continuous tests to see if we change the catalyst, if we change the catalyst-oil ratio, if we use different mixes of traditional fuels and biofuels, what is the coking that we get? Like, what's that residue we're going to get, and how would that impact existing operations to create, usable energy sources?
Okay. Thank you very much. Is there anything else you'd like to say? What's your experience been like this summer? As far as how your life's been, have you enjoyed being here? You think it's a really worthwhile experience?
It has been an incredible experience. I came into the lab thinking that I didn't know how to do these things, and why would I be on this project? I don't know what I'm doing. And Professor Castaldi and all of the supporting infrastructure here at the school, they stay with you. So when you don't know how to do something, you go in and you have a conversation and you figure things out together, and there's such a sense of compassion and understanding for trying and trying again. And you don't get things right the first time, but you keep working, and that's how you learn so much, not just about learning skill sets, but you learn so much about the species you're working with and how it behaves. So I've learned a lot, and it's
Sounds
been
like it's been a great experience.
It has, for sure. And definitely everything takes more time than you think it will take, but once you put that time in and you get that first test that comes out clean and you get this very clean reading, it's an amazing feeling. You feel like you're contributing something to the knowledge of the world.
Okay. Well, thank you so much for sharing your experience with us.